We're happy to have Dave Futer. He's going to talk about the geometry of tunnels.
All right. Thank you for the invitation to speak. It's been a wonderful and really, really delightful week in New York when I learned a lot. So it's a pleasure to be here. Everything I'm going to say is joint work with some subset of these wonderful folks, but it's sort of two different collaborations. So part of this is joint work with Jessica and Daryl, and part of this is joint work with Jessica and Saul. I could put curly braces around this, but that works. So let me start with a couple of definitions. So first of all, for this talk, M will pretty much always denote a 3-manifold, compact, orientable, and with boundary in non-empty tori. And I want to define what a tunnel system is before getting to geometry. So a tunnel system for M is a collection tau 1, tau n of disjointly embedded arcs from the boundary to the boundary. Such that when you drill out those arcs, you get a picture. M minus tau 1, tau n is I'm going to be kind of loose and sloppy with interior versus closure, so technically you have to drill out a neighborhood of those tunnel arcs, but good enough. So, I'll give you a couple examples, if you haven't seen this definition before. At least one of those examples has already appeared in Jesse's talk in slightly different guise. So I'm going to take a complement of a knot or link in the 3-sphere, a link, and I think for the purposes of this conference, the best knot in the 3-sphere is the whitehead link. So here's the picture. I did the opposite mistake. Awesome. I wish that was intentional. Okay, I should be able to do this. There we go. So here's a picture of the whitehead link. And for every crossing, I'm going to add an arc from the overstrand to the understrand. That has also appeared in this conference in Jessica's talk. So take an arc from the overstrand to the understrand at every crossing. Tau 1, tau 2, tau 3, tau 4, tau 5. And then I claim that M minus K union tau 1 tau n is homeomorphic to M minus S3 minus a planar graph, and hence a handlebody. And the way that you see that is you just take every arc and collapse it down to a point. That doesn't change the complement. And then your projection with over and under crossings just collapses to its projection graph, which is a 4-valent graph. So the complement of this is homeomorphic to the complement of that. Is to take a planar graph that complements a handlebody. So the upshot of this example is the tunnel number of a link complement, which is a quantitative velocity final, defining in one moment, is less than or equal, the tunnel number of S3 minus K is less than or equal to the crossing number over K. So let me add something to the definition. The tunnel number of M is the least number of tunnels. So this tells you that if you have a projection diagram with 5 crossings, then 5 tunnels will certainly suffice. In this particular example, it's massive overkill, so you can do much better. So here's another example. M is S3 minus K, and this time I'm going to insist on A being a two-bridge link. And so we draw the same picture in a slightly different way. I realize that it's Friday morning on the last day of the conference. This talk is going to feature a good number of pictures, and in particular, every proof will mainly be a picture and a small number of words. I'll try to have more pictures than words. So here's a two-bridge link. This, 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 this. You have 2 maxima at the top, 2 minima at the bottom, and a braid in between. If you're bored, an easy exercise is to check that this is actually a planar isotopy of the same diagram of the relative link. Now I'm going to take a single arc connecting the 2 maxima. And again, I'm going to play the same game where I modify the graph in S3, but I won't modify the complement. I want to convince you that the complement is a handlebody. So I'm going to take that arc and collapse it to a point. And then you have the crosses of the braid. 1, 2, 3, 4, 5. And the point is that now you have a braid descending down from a point, and you can just start untwisting the crossings of the braid without changing the complement. So I'm going to untwist that top crossing, and then all the rest will be as before. 1, 2, 3, 4. And you keep going, untwisting the crossings one by one until you get a figure 8 graph. So again, you get a planar graph that complements the handlebody. And you can do the exact same game where you have an n for each presentation, n maxima at the top, and you put n minus 1 arcs. So similarly, with n bridges, n minus 1 arcs. So the upshot here is that the tunnel number is less than or equal to the bridge number. So that's it. If you want bounds on tunnel number, this is a much better one than what comes from crossings. That's just a couple of examples to get us warmed up. My real goal is to talk about geometry. Before I do that, I have to say one thing about the connection between this and Hagar splitting, because there's actually a pretty detailed connection, and then we'll switch to geometry. Questions so far? Okay. So there is a deep and, well, actually pretty immediate connection between this and Hagar splittings. Hilbert splitting here in slightly different language. So the way to make it explicit is you let n be a regular neighborhood of the boundary of M union the tunnels. Be a regular neighborhood. And then S, which is the boundary of that regular neighborhood, is a Weber surface. For M, where N is the boundary thickened across 0, 1, union 1 handles for the tunnels. It's pretty much the definition of a compression body. If you have not seen the definition of a compression body, this is a definition. You take a surface, you thicken it, and you attach some one handles, possibly disconnected surface. And the rest, which is M minus N, is a handlebody. Using the definition over there. So a tunnel system naturally defines a Hilbert surface, and you can generally go back. So for going back from Hilbert splitting to tunnel systems is that given a Hilbert splitting H along the surface, where H is a handle body, the one handles of G in a tunnel system here there's maybe some issues of uniqueness. So if the genus of the surface is 2, generally speaking, maybe I could say that in the tunnel system, tau 1, tau n, where the genus of the surface is 1 more than the number of tunnels. You can see that even in these examples where if you take a single tunnel, then you'll get a genus 2 surface. It comes from a figure 8 graph. So if the genus is 2, a tunnel tau is uniquely determined by S. And if the genus is higher, then it's not quite unique. Greater than 2 in the tunnel system. Now 1. Now n is determined uniquely after handle slides. What's a handle slide? It's one of these moves where you slide a handle over another handle. So here's one unknotting tunnel, here's another unknotting tunnel. And we're thinking about the surface that you get when you take this graph and thicken it. And the point is that you don't change the surface if you just take one of these endpoints of tau 2 and drag it over tau 1. Tau 2 and drag. So you can do these moves and up to these moves. So far, so good? All right. So geometry. questions? So from now on, I'm actually going to assume that our manifold is hyperbolic. From now on, assume because it's compact and has torus boundary, that means that the hyperbolic metric is unique to isometry. And you can start asking exactly what these tunnels look like, geometrically in this unique hyperbolic metric. So here are some questions posed in 1995 by Adams and Weeks. The first question is every tau I isotopic to a geodesic? They really asked this question only when there was a single unknotting tunnel, but you can generalize it to multiple unknotting tunnels. At least it's harmless to ask the question, although maybe it's too much to hope for. So one remark is that it's always homotopic to a geodesic because the tunnels are topologically non-trivial. If there are no redundant tunnels. If one of them is just homotopic into the boundary of the manifold, you can just throw it away. It's unnecessary, but generally, they'll always be homotopic to a geodesic. But of course, homotopy and isotopy are very, very different.
Excuse me.
Yes.
So these tau-I's are arcs. They're
Yes.
not loops.
Right. Right.
It's geodesic is a closed.
No, it's not a closed geodesic. It's a geodesic from cusp to cusp. Right. It's a geodesic with endpoints and infinity. Does that make sense?
Properly isotopic.
Yeah, properly isotopic. And a second question, which is perhaps a stronger form of asking the same question, and this is really kind of an example of what Nathan earlier in the week called, quantitative rigidity, or WYSIWYG topology, is we want these to somehow reflect the geometry in a particular way. So is every tau I isotopic to a canonical geodesic? I should say what canonical geodesic means, although one great advantage of speaking late in the conference is that almost everything has been defined for you. And this is very closely related to something that Fang talked about yesterday. So, what are canonical geodesics? Edges of the thing called the Delaunay decomposition, or for cusp manifolds itself, it goes by the name Epstein Penner. Decomposition of M. So I'll define this via a picture in the spirit of being kind of a little bit loose and informal on the last day of the conference. So here's the picture in dimension 2 because it's too hard to draw a picture in dimension 3. So here's your hyperbolic manifold in dimension 2. And maybe have some genus and some cusps. So this is S. You lift it to S tilde, which is the hyperbolic plane. And these cusps will lift to a collection of horballs in the hyperbolic plane. So there's one horball here, there's another one here, another one here, maybe there's a little one here. And to each of these horballs, you associate a region which is all those points in the hyperbolic plane closer to it than to any other horball. So these points are closer to here than to here. So here's each one, and here is a region R1. R1 is that points closer than H1 and horoball. This gives you a decomposition of the hyperbolic plane into regions. This is exactly the Voronoi diagram that Feng spoke about. Are these regions cut up by the blue geodesics, and dual to it is the canonical plane position. It seems that all these things have been discovered multiple times. It's a very natural construction in topology. So the Epstein-Penner decomposition is also called Delaunay. The Voronoi diagram is also called the Ford domain. These have all been rediscovered multiple times. So the difference between the first question and the second question here is that there are infinitely many geodesics, but there's only finitely many canonical geodesics. So you somehow want these really nice topological objects, namely the tunnels, to somehow correspond nicely to canonical geometric objects. Yeah, Robert?
So the Epstein-Penner decomposition will, the Delaunay regions will depend on your choice of horoball.
Right.
How far
Okay.
out it is. But does the Epstein-Penner decomposition depend on that?
In the same way, yes. Okay, very good question. So here, there's the word canonical sort of suggests that there's only one. And it's really truly canonical when your manifold has a single cusp. Because what happens then is that, yeah, it depends on the choice on the size of the horballs, but when you have only one cusp, as you expand the one cusp down in a surface or the three manifold, all of these horballs will expand equivariantly, and being closer to it than to any other lift is a property that's preserved when you change the sizes of all of them simultaneously. When you have multiple cusps, then you can change the size of one relative to another, and then, then what I call canonical is not completely canonical, although it's the theorem about Kiyoshi that there's only finitely many combinatorial types. So even though somehow the parameter space is non-compact, you can make one of these horballs as tiny as you want. You can, if there's only finitely many combinatorial types. So that's a very good question. So this question is an example of WYSIWYG, what you see is what you get, or as Nathan called it a couple of days ago, quantitative. So those are some questions. Let me start giving you answers. known, at least for unknotting tunnels with a single tunnel arc. For single. There's a tunnel arc that all by itself gives you a handle. So here, tau is a tunnel of M, which implies that M minus tau is a GTiNY2 handle body. And of course, to cut up your manifold into a handle body, you have to connect all the boundary components. So that means that you only have one or two boundaries in this special case. So boundary M is 1 or 2. So let me first address the first question is how geodesic. It's a question that's at this point about 18 years old, and it's still open, but I can tell you what's known so far. The first answer is yes, if boundary M has two tori, if you have two cusps. This is a theorem of Adams in the same paper where he asked a question. And the argument is too pretty to not sketch it. So here's a schematic picture proof. I'm trying to hold myself to the promise that all proofs will be primarily a picture in a very small number of words. So what's the schematic? Here's one boundary torus. Here's another boundary torus. And here is your tunnel. Connecting them, let me sketch a picture of the Hayguard surface corresponding to this tunnel. Hayguard surface S, it's GTiNY2. What's special about GTiNY2 is that you have a hyperelliptic involution. There is a unique involution of the surface that sends the isotopic class of every single curve to itself. In particular, the isotopic class of the boundary of the disk dual to the tunnel will be sent to itself. When you have two different boundary tori, the disk that's dual to the tunnel cuts your compression body into pieces, in particular the boundaries, separating curves are sent to themselves with orientation by the hyperelliptic involution. So that means that, it's the name, so phi, the point is that hyperelliptic involution. Phi preserves the tunnel pointwise. And then Moscow and Waldhausen tell you that phi is isotopic to a hyperbolic rotation preserving an axis. So tau is isotopic to that axis. So what's special here is that your involution is going to send the tunnel to itself with orientation preserved.
So not only you need two tori, but you need the arc to go from one torus to the other.
Yes, but an unknotting tunnel has to, by definition. You want the complement to be a handle body, so the other side can't have any extra boundary. Yeah. There's a slightly more general context, right, where you split into two compression bodies, and then that argument won't work. Sorry?
Yeah, okay, fine.
But that's exactly sort of what breaks down in the case of one torus. You still get a hyperelliptic involution, but now that's going to reverse the orientation on the tunnel. Okay, one answer. A second answer is that it's true for the example that I showed you at the beginning. So yes, if M is a complement of a 2-bridge knot, this is due maybe in pieces to Adams and Reed. 96 for some of the tunnels, and I worked it out for the rest of the tunnels. But really, it should be seen as kind of a very old result. But of course, 2-bridge knots are extremely special. They're a very, very special family of examples. In fact, they're so special that this second, much stronger question is also has a yes answer in that family. So, Q prime, sort of the canonical question, also has this answer. For these, and this is due to Yoshi, Sakuma, Wada. Yamashita, and that's what I give it to. And let's say about. So 2-bridge knots are very special. For those guys, they're all edges of canonical. I won't say very much about the proof of this. And yes, sorry?
I mean, isn't it getting to himself?
He really did the canonical thing in his thesis by himself. I could try to attach myself to him, but it's really his theory. So this was in his thesis.
It's his turn, but it's your job.
Yeah, okay, so I can lie up to the ability of the audience to call me on it. And I have a stinking suspicion that if I said the opposite, then Francis's comment may have been the opposite. So, and the third answer, which is sort of what I want to talk about a little bit, is that it's true generically. This is Daryl Cooper, Self, and Purcell years ago. So I have to tell you what generic means before I move on to multiple tunnels.
The yes here is for both, or just for
Just for the geodesic question. The canonical geodesic question, as I was sort of hinting, is really too good to be true. I'll actually give you a generic answer to that question as well, but it's going to be sometimes yes and sometimes no.
And this is still for one tunnel?
This is still for one tunnel. I hope to be able to say something concrete. Okay. So here's a definition. So M, a two-cusped hyperbolic manifold. So that means the boundary M is the union of two tori. Again, I'm being sloppy with the interior versus the whole thing. Is T and K. Tori. And then pick a slope view, which is to say isotopic class of essential simple closed curve. On one of the tori, and we say U is generic if two things are true. So first of all, want the slope to be sufficiently long, in some choice of Horobal neighborhood for t, really, if I don't quantify sufficiently, then I don't have to say how big the Horobal is. And not only that, but the shortest longitude for it, which is the shortest curve that intersects it once, is also sufficiently long. So the shortest longitude, mu of course is going to stand for meridian, lambda of mu, i.e. the shortest curve, intersecting once, is also sufficiently long. And then we're going to consider I apologize for doing this, but I think M only appears once. I'm going to start X, down at X, and the manifold that I actually care about is, of course, the Dane filling along this very generic curve. So M is X of mu. So I want to justify why it's generic. This justification is in terms of the curve complex, which has been very adequately discussed in this conference. So here's the exercise, is that in the curve complex of the torus, which is very graph, a set of non-generic slopes is bounded diameter, but the whole thing is infinite diameter. It's a quasi-tree, so it's hyperbolic. So somehow, if you forget about a set of bounded diameter, almost everything else is still available to you. That's why I'm calling it generic. I probably shouldn't spend much time discussing the curve complex, and it's not really germane to the talk. So if you know what that means, great. And if not, look up the definition from Saul's talk, modify it appropriately for the torus. This is an easy exercise. And something that's deeper than an exercise, but is also true by the work of Futer, is that it's a theorem of not here. That's Joseph Long, years later, is that if X is constructed by Haggard splitting, G and H, so H handlebody is constructed via a random walk in the mapping class group. Then S is the unique minimal genus surface. Then S is the unique minimal genus Haggard surface. Which means that if genus is 2, there's a unique unknown. So if you start with a generic cusp two manifold, two cusp three manifold constructed in this way. Generically, you'll have a unique unknotting tunnel, and if you take a generic contained filling of it, you'll still have a single unknotting tunnel and a hoops. Yes.
So is it true that the non-generic are finitely many?
No, no.
Oh, is
They're infinitely many, which means really that
okay.
you have to jump through some hoops to say what generic means, and it's very much dependent on your model of what reality means. You know, how do you enumerate three manifolds, right? There are countably many that are generic, and there are countably many that aren't. So, but somehow, I'm claiming that this is a fairly reasonable way to construct kind of random things. This particular model of genericity was explored a lot by kind of Nathan Dunfield and Bill Thurston, who showed, you know, generic three manifolds constructed this way are rational homology spheres, for instance. So I mean, you can argue about what it means to be a random three manifold, but this is one of the natural models. But it's definitely not true that, you know, this is all the finite.
Unlike hyperbolization.
Well, even hyperbolization in dimension 3, as you well know, has more than finitely many non-hyperbolic three manifolds. There's more than finitely many non-hyperbolic knots, but yet hyperbolic knots are still generic, so it's in the same sense. Hyperbolization in dimension 2 has finitely many exceptions, but in dimension 3 there's no.
So fixing
maybe
X hyperbolic, all but finding many feelings are hyperbolic. Right?
Oh, yes, for that, yes.
Okay, that's
I was talking about this, yeah.
All, yeah.
For that, yes. That's right. And there's also infinitely many exceptions here, although, again, one last thing I want to say is that tells you that M, which is this generic contained filling, also has a unique homology. And in fact, it helps to draw a picture. So what's the picture? Here's your, if there was too much technicality on this board and you're not used to the technical verbiage, then ignore the whole discussion of what generic means and believe me that it's generic, and just pay attention to the following picture, which is somehow what's going on. Okay, so here's X. It's a manifold with two different torus boundary components. I'm calling one of them K, one of them T. The tunnel I'm calling sigma. Then I'm going to fill one of the two boundary tori. So here's how I filled it. Here's your meridian. And what's the sort of unknotting tunnel here? Well, you follow along sigma, you go once around the longitude, and then you head back. So again, easy exercise. Work out that if the complement of this is a handlebody, then the complement of this is also a handlebody. You want to first drill out the core, which is a copy of the longitude, and then drill out. So this is M. And called tau. State theorem, I think, is also going to answer your question, Walter, about what happens for. Oh, I'm about to erase this, so I'll stare at it for one more second. Right? You want to know whether every tunnel is isotopic to a geodesic, and you want to know whether it's isotopic to a canonical geodesic. film. Myself, Jessica. So let X be a two-cusp manifold with sigma M X. So mu a generic of X with the associated channel tau. And then here are the answers to the questions of is it isotopic to a geodesic and is it isotopic to a canonical geodesic? This is one. Tau is isotopic to a geodesic. Under these hypotheses. And second, tau is isotopic to a canonical geodesic. Well, if that was the full statement, then one would be unnecessary, but this doesn't happen all the time. It actually happens if and only if the tunnel in the two-cusp manifold that you started with is the unique shortest geodesic. Cusps. Sometimes it is, sometimes it isn't. So this will give you infinitely many examples where a tunnel of a one-cusp manifold is not canonical geodesic. So I'm going to say that as a remark. To this infinitely many examples. Before we did this, there was only one example. So it was known before us that such examples existed, but there was only one example known. So, we can give you infinitely many examples. We can give you infinitely many examples with one canonical, one non-canonical analysis. That really strong question was too much to hope for. Let me give you a 1 minute picture proof for part one, and then I'll say something about the questions. So, part one is here's the kind of hyperbolic geometry analog of the picture over there. You have two cusps. You're filling one of them, you're not filling the other. So here's, you're not filling. And here's another copy of the one you're not filling. Actually, let me turn a little further along. Here's the sigma. This is K, that's pure keeping. Maybe if you're blue. And what's going to be your tunnel after filling? Well, you follow along the old one, you go along the longitude, and then you come back. So here is your tau. And then here's the geodesic in its homotopy class. And I took an example where this longitude is very, very long. When that longitude is very, very long, this geodesic is going to stay very close to this vertical segment, and very close to this vertical segment, and otherwise it's going to spend all its time in this oroball. So when that is long, the geodesic class tau stays very close to sigma, or else deep in. So this picture is in the unfilled manifold. You have to draw the corresponding picture in the filled manifold, but somehow you want to say that the geometry doesn't change very much, and then you want to quantify the very close and actually carefully say that you can push through these controlled parts and turn the homotopy into an isotopic. So this is the very polite picture, but actually making it work is sort of where the hard work is.
Could you push that forward?
Oh, sorry. All right. 5 minutes for multiple times. State two theorem. One is due to Jessica Hender's student Stephen Burton. The other one is due to us. And I'll draw a picture. So first theorem. Burton. Jessica Purcell. 13 says you pick any n and you pick any epsilon. There exists a one cusped hyperbolic manifold M, any in n epsilon, with tunnel system L1, Ln, such that L1 up to n-1, so all but n-1 of these have geodesic representatives that are epsilon close to self-intersecting. The reason this is relevant to the question is when it's very, very close to self-intersecting, this is what the geodesic looks like. And then the actual tile that you started with, well, you don't know if it's here or if it's here. It's, it's very, very close. It's somehow a very subtle question. And, if you somehow control what side it's on, well, then it'll have to cross itself to actually be a geodesic. This is strong evidence that there should exist non-geodesic links. And they prove this by geometrically finite structures and compression bodies where the tunnels actually do self-intersect. And the second theorem, so 13 is that they actually give you examples that are not geodesic. So let M be a cuspy manifold, doesn't matter how many cusps. Cusp B manifold. S a rebar surface. You do want to handle that on one side. And genus strictly greater than 2, so we won't do this for genus 2 or a single unknotting tunnel, but everything else works. And then for any setup of this type, there always exists a tunnel system. There exists a tunnel system. Tau. So it's G minus 1. This is genus for M, such that each tau I is not isotopic. So let me draw the picture proof for this one. The two-word proof for that one is do handle slides. When you have genus higher than 2, you can do handle slides, and that's enough to mess things up. So here's a cusp. Here's another lift of the same cusp or a different cusp. Another one over here. So let's see, where are the colors? Here is one. Here is tau 2, and here's another lift of tau 2. And I'm going to take this and I'm going to drag it around until it gets messed up enough that it can't be isotopic to the geodesic. So I'm going to do take this tunnel here, I'll drag it along here. That. I've taken it and I've dragged it over the other tunnel. So far, I haven't messed it up enough yet, but there's another lift over here that does that. I'm drawing this in a different color, only to indicate a slightly different lift, but hopefully brown looks sufficiently similar. And then I'm going to take this, so this is this tau 1 prime, and this is also another lift of tau 1 prime. And then I'm going to keep dragging it along the horizontal and over tau 2 again. So there's this. There's this other lift. That. Smidgen more. I apologize for having a couple minutes over. So this, that, and now I'm going to take my red one. It's already gone all the way over here. I'm going to drag it here, and I can slide it back along the blue one down this way, but now it's becoming intertwined with a different lift of itself. So here's my of course, this other lift of itself is also then over here and get intertwined and so on. And now if I take this red thing and I try to pull it tight to a geodesic, it's going to want to go this way, and all of these twists that I've done around a different lift of itself are going to have to snap. And that means that it has to cross through a different lift of itself in order to become geodesic. And then you can play the same game in reverse. Just draw a copy of this picture with tau 1 and tau 2 interchanged. This is going to look horribly messy, but you can still drag things over enough to make the other one not geodesic. So you can just play these games by turn. All right, I'm a couple minutes over. Thanks very much.
you're showing that for this particular choice of tunnel systems, why can't you pick a different tunnel system that doesn't have this?
Well, the point sort of is that
In
you
other words,
can.
your theorem is an existence statement about this tunnel system. but there
My
is-
theorem is that there exists a tunnel system. Well, in fact, there exists a tunnel system for every Haggard split. Right? Doing handle slides preserves the Haggard surface, up to isotopic, like everything is doing. So for every Haggard surface, of genus strictly larger than 2, there is a tunnel system. And the point is that you start with one, maybe the initial one looks very nice. And then even if this picture didn't look very nice, you could, it would schematically still look like this. Maybe tau 2 was already not isotopic to a geodesic, and it was already this big messy thing. I could still drag my other tunnel over it. So the point is that even you pick a Haggard surface. So if we're playing a game, you hand me a Haggard surface, you hand me a tunnel system, and I tell you how to mess it up. So I can mess up your nice, pretty setup. Ian?
So if you have a geodesic, then it's a knotted hyperbolic. So you can find construction tunnels where some of the arcs are knotted and you can cover and therefore not geodesic.
Probably, especially if the if the complex length of that geodesic had some rotational part, right? So then if in the universal cover, going around it also and then twisting a little bit, go around enough times, probably I'm knotted up. If I understand your question correctly, are you thinking about a closed geodesic or like a?
So I'm just saying, if you have an arc that's knotted, it's not at the top of the geodesic.
Right.
So why can't you just take a tunnel system where some of the arcs are knotted?
Well, you have to find one.
So,
Right.
okay, so I guess,
You have to find such a thing to start with.
well, just tie a little knot and then add some other arcs that then do it.
Well, I mean, one could add minimal to the,
Yeah.
Right, S might be
this
minimal.
is for any, so in particular it covers the case of minimal, right? You could take a minimal genus sequence. You could take, the unique minimal genus sequence splitting.
Okay, well, that's more compelling than
I mean, I'm trying to state the theorem and say so that the hypotheses are as weak as possible. This is for any Haggard surface.
And then you, oh, okay.
Yeah, this is for every Haggard
So
surface.
it's, do not allow it.
Yeah. So, in the adversarial game, you pick the cusp manifold, you pick the Haggard surface, I tell you how to mess it up.
Okay, so you could ask whether, and you say it in arc, the knotted percentage of the universal cover, the complement is knotted, it's isotopic, the collection of straight lines in arc 3.
Mhm.
You could ask for whether there's an arc that's knotted in that sense too.
Yeah. Isn't this the same? I believe it is.
these are just linked.
Oh, I see. These are just linked. Or you want each one itself?
Yeah, the collection, the unit of all three images might be knotted in the sense that the fundamental group of the complement's not free for
That I think can't be true for exactly fundamental group reasons, right? The fundamental group downstairs is free.
Right, but adding some more arcs maybe becomes.
Oh,
free.
okay. Well, I mean, if the things you add are tunnel arcs, right, then the complements of handlebody fundamental group is free, and then, upstairs it's just some, infinite rank free subgroup of your free group.
Yeah, but after you remove some premiums from some of the arcs, then it might not be free.
Maybe we should talk afterwards, so let people have a little break.
Other questions? Do you have any distinct connection between this work and unknotting number?
Despite the similarity in name, I don't. That could be just my lack of vision.